My apologies. This is an application of work in which I've been involved for some time. It turns out that systems of conservation laws with entropies admit a canonical form, typically an extension of the familiar symmetric form, which is very good for representing the symmetry group as well as the existence of the entropy set. Now, using this, you can do some things. For example, there was a simple homotopy between Lorentz transformations and Galilean transformations, and you can use this to find a homotopy between a given Lorentz symmetric system and a Galilean symmetric approximation thereof. So I'm going to apply that now to reconsider MHD models by taking the relativistic Euler-Maxwell system as kosher and then saying, can we simplify this to get rid of the characteristic the light speed characteristics in particular, end up with a more manageable system, and see what we get in the way of candidates for MHD models. Okay, well, if you do that, now let's see, avoid the self-destruct here. All right, we want to reconsider MHD models. When we neglect terms, obviously this will limit the region of validity in phase space. And if these systems, we can't begin to prove well-posedness, either of the original system or of the approximations. So the question is, what properties are you going to want on the approximate systems? Well, okay, we anticipate weak solutions. We're going to need an entropy condition to have any chance of admissibility. So we want something like the thermodynamic Euler entropies for these systems. In addition, we want expressions of conservation of total energy and momentum. We want the symmetry group within the region of validity. This simply will mean exchange of Lorentz symmetry for Galilean symmetry. And in cases of parameter limits, such as when the charges of a fluid go to zero, the interaction with the electromagnetic field should disappear, and we would like to see that appear in the model. Okay, now, no, I need to point this here. Okay, now for Euler, there's absolutely no problem in doing this. You start with the relativistic system, you go through the machinery, and you get the familiar compressible system. The force and work of the electromagnetic field on the system are well known. Now, a notation here. First, the letters like this are the thermodynamic variables from the familiar notation, and the Roman letters, this, are the electromagnetic variables. Normalization is used where all of the electromagnetic variables have the same units. So C is just the unit of velocity, it's the speed of light, invariant, etc. Okay, so for Euler, we have neglected the velocity with the fluid velocity with respect to the speed of light, the pressure over rho c squared, and the internal energy over c squared. This is all well known. Okay, the thermodynamic entropy survives simply because of the specific form of the balance terms. What is worth noting is that the Galilean symmetry requires that the electric field is not invariant. It changes this way if you haven't seen that before, and there's no problem with the charge neutral limit. Now, Maxwell's equations are more interesting. This is an example where you get something non-trivial from going through all of this machinery. Here's Maxwell. We take the linear approximation, so the displacement is proportional to the electric field and the magnetic induction is proportional to the magnetic field. Of course, you need conservation of charge in the usual form. Now, this system is Lorentz symmetric for epsilon equals mu equals 1. And now all of the work, for which I apologize not giving, tells you that if you want this system to be Galilean symmetric, you must have the product of the dielectric constant and the magnetic permeability must vanish. Beginning if and only if. That's the theorem, and I won't try to prove that here. However, the write-ups are available for those who are glutton for punishment. So there are two ways of getting Galilean symmetric approximations of Maxwell's equations. One is to neglect the magnetic induction. And if you do that, you get a system here for you get a boundary problem for the electric field. I'm ahead of myself. When we try to replace Lorentz symmetry with Galilean symmetry, there's going to be a problem with respect to the light speed characteristics, which are being neglected. Now, the way you can neglect something moving very fast is to assume it's in equilibrium. But that means that we anticipate getting a boundary value problem for at least one of the electromagnetic field components. So here's an example. From this, you get a boundary value problem for the electric field. The magnetic field now satisfies this. Now you can take the curl of this equation and get one equation for H, but you don't know what div H is going to be. But in this case, you can take it 0 if you want and not lose the symmetry condition. So well enough. Okay, again, we get the momentum and energy of the electromagnetic field, assume familiar forms, etc. Say the same, the partial, some of the terms that you get from the Lorentz symmetric term, these equations are formally obtained by just taking products of the primitive equations with, in this case, the electric field, similar expression for the work of the electromagnetic field. Again, formal products of the primitive equations with the thing. Okay, now the alternative is to neglect the electric displacement and take the magnetic permeability equal to 1, which means you're ignoring the electric displacement and taking H equal to B. And this approximation is very much less attractive. You save the solenoidal magnetic induction, and you save Faraday's law, but now this should be div D. You need charge neutrality. And you ignore the displacement current, so you recover the original Ampere's law. In this case, conservation of charge is just div Q equals 0. Okay, we have now the electric field is highly ambiguous. We know that E satisfies this equation. If you know Q, then you have this equation, but you don't know div E very well. And div E is not, you'd like to take equal to 0, but you can't because it's not invariant under Galilean transformation. Here's the explicit expression. If Q doesn't vanish, you can't have E vanishing. But again, we have expressions for the force and the work of the electromagnetic field on whatever. Okay, now we'd like to couple one of these Maxwell approximations with the compressible Euler subsystems and obtain models. The procedure for doing that is easy enough. You select which of the Maxwell approximations you wish to use on the basis of what am I willing to neglect. You relate the force and work of the magnetic field on the fluid or fluids in order to conserve energy and momentum. You specify the net charge and current densities in terms of the fluid variables, and then you have to have an algorithm for the missing electromagnetic field component depending on what you've done. For a single fluid, this is very easy. You just equate the force and the work that conserves energy and momentum. For a charged fluid, alpha is throughout the charge per unit mass, so we know the charge of the fluid and we know its current. We know the current, physics 101. And if we use now the electrostatic approximation and take epsilon equal to 1, mu equal to 0, then we just have the force and work depend on the electric field. We get a Poisson problem for the electric field, no problem here. And we find that the only terms we have neglected are depending on the magnetic induction and have a C in the bottom. So you hope that those are small, and this is a perfectly reasonable approximation as long as you can ignore the magnetic induction. But if you ignore the magnetic induction, you obviously aren't talking about MHD. If we want the magnetic force on the fluid, then we have to use the second relatively unattractive Maxwell approximation, and that's where the fun begins. Again, we try to conserve energy and momentum by equating the work and force of the field with that on the fluid. And when you do that, you just set the fluid force equal to the electromagnetic field force. You find, and use the formal expressions for these, you find that you recover exactly the Lundquist momentum equation, and you get an explicit expression for the electric field, which if it weren't for this term, it would be the same as Lundquist. There's an extra term, and I'm going to refer to this model as the modified Lundquist because of the extra term here. But again, giving the electric field explicitly in terms of the magnetic field and the fluid density. Okay, again, equating the work on the fluid with the work of the electromagnetic field, we recover exactly the Lundquist energy equation. So we have almost Lundquist, And as again with Lundquist, keeping Faraday and assuming the magnetic field is initially solenoidal, it will remain solenoidal. So there's no problem with satisfying div B equals 0. However, in this formulation, we have abandoned identifying the net charge with the fluid charge because alpha isn't 0, alpha rho isn't 0, and we need charge neutrality. And we've also abandoned relating the fluid current with the electromagnetic current. Because if this were true, then curl E, you can go through this. This is a mistake. This should be C here, not C squared. We have an expression for curl E, which is equal to this, and the expression for E doesn't in general satisfy that. Furthermore, there's a problem with regularity. All of the work on Lundquist systems deals with these complicated electromagnetic shocks, et cetera, where the electromagnetic field becomes discontinuous. And if the electromagnetic field is discontinuous, it is by no means clear that these formal products, which are used to obtain the energy equation in particular, are valid. So there is a real question as to whether to what extent is this mathematically kosher. Now, it turns out that these problems are remarkably easily overcome. The trick is to introduce two fluids. To say that, well, let's regard our original fluid as positively charged ions and say if we have such, then there are going to be free electrons. So everything with a star on it refers to the free electrons. And now if we do that, the charge is the sum of the two charges, and setting E equals 0 simply means that the two fluid densities are linearly related. And identifying the total current with the sum of the electron and current simply means that Q is curl B, so we know the electron velocity in terms of the other variables. So we know rho star and U star explicitly in terms of the ions in the magnetic field. Furthermore, with these identifications, automatically it comes out that the electromagnetic force is divided between the two fluids, and the work is divided between the two fluids exactly as we want to conserve momentum of electron. And from this, div Q has to vanish, and that means that the equations for conservation of mass of the electrons and for the ions are equivalent. If you satisfy one, you automatically satisfy the other. Now, the neglected terms are all the same ones from the relativistic. Okay? We have neglected the displacement current. Here it is. And this is the problematical one. We have neglected div E. And div E isn't even invariant, but the term has an S over C, and hopefully it's small. The question of whether this is going to be valid is going to depend on how big div E is. Okay, so we want to use Faraday and the momentum equation, which we want for the electrons, to find E. And it turns out that can be done. This is the nice result here. Curl E is this. You go through and you get something with the minus sign. This piece is positive times E plus a bunch of garbage, which collects all of these other terms which you think you know. So we get a boundary value problem for the electric field here, which is elliptic, but not uniformly elliptic. And there's a regularity problem because for weak solutions, these xi and zeta here are not going to be continuous. There are derivatives here, and it's not at all clear that the singular part of this guy in particular can be matched with the singular part of this. So solvability of this problem for E is by no means clear. But here's our dynamical system. We have the three equations for the ions. We have the electron density and velocity given explicitly. We have to include the energy equation for the electrons, Faraday, and then this boundary value problem for the electric field. And if you do that, even weak solutions will satisfy the equation for conservation of mass and conservation of momentum for the electrons. Okay, so the first we need a theorem about solvability of that boundary value problem, and here it is. With specifying curl E plus a constant times E, it turns out you want to specify the tangential components of E on the boundary, but the normal component remains to be determined. But there is a unique E with these boundary conditions. The problem is, and here's the regularity, that you need this div zeta to be H0 minus 1. Now that's one derivative too strong, because if zeta is only L2, putting two derivatives on it, you get -2 here, and so we're in trouble on this particular problem. But if you make this strong assumption, then indeed there's a unique E. It satisfies the PDE, and the E and its curl are in L2, but div E is God knows what. Okay, so the next we need a lemma on when can we recover this, and it turns out that it comes out very nicely. If you have a nice model, everything is smooth except for some shock curves, which may intersect and may reach the boundary. That's perfectly all right. But outside of the shock curves, everything is well behaved. And you satisfy the mass and momentum equations up to time t. Then at time t, this div zeta is indeed as smooth as you want. And the proof uses the Rankine-Hugoniot conditions. You need a smooth enough solution that you have RH conditions satisfied. Then you get div zeta, the jump in div zeta, in the normal component of zeta vanishes, and that's what you need, doing all the integrals very carefully to show that indeed div zeta is as smooth as you want. So, okay, now conservation of momentum and energy. We saw that there was a regularity problem now, but now we're doing better because B is smooth. See, curl B is Q and div B is 0. So if Q is bounded, then B has bounded first derivatives. So there's no trouble with that. And we got E and curl E in L2. And therefore, these formal multiplications are justified. And as a result, you have an equation for conservation of total momentum and an equation which is too big to go, but here is the full conservation of energy, ions, electrons, and the fluid. Finally, we have a result if alpha goes to 0 and we take alpha star fixed, if everything is bounded nicely, uniformly, and the initial data has curl B. See, curl B is the current. So if you're going to have the charges becoming neutral, you have to have 0 current in the limit. So you make 0, then the body, the force at work terms also go to 0. So the parameter limit as the fluid, as the ions become, as the molecules become neutral, non-ionized is in. Now finally, we can use this formalism to recover the modified Lundquist model. If we think of ions and electrons, well, even if this were hydrogen, that's 1800 alpha over alpha star is 1 over 1836, I think the number is. For most people, that's small compared to 1. So we can just say, all right, if the electrons are so much more sensitive to the electromagnetic field than the ions are, let's just take the force of let's take the electrons in quasi-equilibrium with the electromagnetic field and say BF star equals 0. If that's true, then here's BF star is proportional to this, and then we get exactly the same expression for the electric thing that we got for the plasma model. So if this is true, then here's E, and U is this. So we get exactly the same expression for the electric field that we had for the modified Lundquist. But in doing so, we have ignored this, the electron momentum and the electron energy relations. These deficits will have to be small for this to work. Now, if you do this, then the question comes, what about the regularity of the electromagnetic field, and do you still maintain a valid expression for conservation of energy? The answer is this is amusing. End on a punchline here. Take the simple case. We have a shock normal to the x1 axis, and it's a real shock. So we're going to assume no jumps in the tangential velocity components, and ignore the x2 and x3 derivatives. So it's just an ordinary planar shock. Now B1, as is thoroughly familiar from Lundquist, the normal magnetic field will be continuous. It will be constant, in fact, and nearby. And we use Faraday then to find the equations on the tangential components of the magnetic field. Now, for ordinary Lundquist, as is well known, you get an equation like this. You get this ordinary continuity equation with a bounded right side here, and that means for a shock of speed sigma, as is well known, the jumps in sigma times the jump in the tangential components is just the jump in the normal velocity times that. So the tangential magnetic field components will develop discontinuities. And this is what we see in the fast shocks, slow shocks, et cetera, identified with Lundquist. If you go through all of this for the plasma model, right, all of the total result is just to take this U1 outside the derivative. And that means that now B2 and B3 will remain continuous, and the jump discontinuities will occur in the first derivatives. Okay, so indeed, the plasma model does better than Lundquist on regularity of the electromagnetic field as we suspected would. Now, for this modified Lundquist, you get the Lundquist term, here it is, plus another term. See, modified Lundquist is not a first-order system of conservation laws because of that extra derivative in the electric field term. So here's what it is. You get this messy-looking term, but a quick look, you can see this is a Schrodinger regularization of this, which is one way, not the usual way, but a possible way of improving regularity of the solution. So if B1, if the normal magnetic field is not 0, then this will be the RH condition on the magnetic field. And you see that the jump discontinuity in the product of the normal derivatives of the times rho, this is discontinuous, so these are discontinuous, and this jump is proportional to the, but B2 and B3 will be continuous. So this modified Lundquist has a chance to be valid, even for weak solutions, if the normal magnetic field is non-vanishing. Okay, it's 5 minutes, right on schedule.